We're very happy to have him back. Today he will tell us about the lead front bootstrap for Chern-Simons matter theories.
Yeah, many thanks. So, wanted to say it has been a while since I last time gave talk here, but we made a deal. So all this semester I'm giving talks on Monday. So it's very cheap.
He's getting his money's worth.
Yes.
For sure.
Okay, so the talk will be about a completely different thing on the first side. But I'm not giving talks unless I can say a few nice words about higher spin, so at the end I will have to say. But the plan is that first I will have to tell you what this word means, Chern-Simons meta theories, and why they're so nice, and what's interesting about them, Chern-Simons meta theories. And the second part, what's new, in the sense why this light from Bootstrap came about, and what you can achieve with that. So, Chern-Simons meta theories are families of conformal field theories that exist in 3 dimensions, and there are many theories of this type. You can have them with fermionic matter, with bosonic matter, with supersymmetry, with matter in different representation of your gauge groups, and so on. So there are simple models of this type, for example, the famous Ising or Ising model belongs to this set of models, even though you don't see any Chern-Simons term there, but it's kind of degenerate member of the same family. And so what's nice about these theories is that many of them are known to describe real physics, which is good sometimes. And because of this Chern-Simons interaction, in general, the parity is broken, but that's not a problem, even if you describe physics. And also, what's interesting is that it was discovered a few years ago that there are many dualities that these models have. And the most, so sometimes models with fermionic matter are dual to models of the same type, also with fermionic matter, but with different values of parameters. Bosons are dual to bosons, but the most interesting type of duality is when bosons are dual to fermions. So you can have models, Chern-Simons plus bosonic matter, and they describe exactly the same physics in the usual QFT sense, like anomalous dimensions, correlation functions, and so on. So they give you exactly the same observables as Chern-Simons theories with fermionic matter. So this is the most interesting duality, and it also survives in the large n limit. So in my talk, I will be working with large n things, mainly because I came from like Eddie's description of all these theories, and where 1 over n plays the role of the bulk coupling constant. So you have a meaningful weakly coupled gravity description of all these guys whenever n is large. That's why I'm interested in the large n, while of course it's fair to say that Ising model is n equal 1 case, and so large n is opposite to the, say, Ising model. Yeah, you can add supersymmetry to these models, and then they go all the way to ABJ or ABGM theories, but I will be working with so-called vector-like models. They have less fields, and there are some specific features of these models that should make them solvable in some limits at least. Okay, so all these theories are interacting, and it's hard to compute anything in them, but there are 2 very degenerate points where you just have free CFT, and you don't even need Chern-Simons. So the simplest one, which I call free boson, is just this. And you can compute everything you can think of, like correlation function, just by weak contractions. So it's the most boring CFT. So, but I will be interested in very specific operators here, which are called higher spin currents. So the first member of this family is not actually a current, it's just phi squared. Then, depending on whether you have, say, UN or ON, so you can put some index here. So there are 2 basic options. You have ON vector, or you have phi bar, phi I, which vectors of un. So, for example, for un, you can get a singlet current here by the standard formula. So it's conserved, and then, okay, you have, so I start abbreviating the indices. So if you have two derivatives here, distributed in the right way, then you can get stress tensor. It's something with two derivatives. But this family is infinite, so if you have phi bar as derivative phi, then you can make it into conserved current. So which means that you should have some infinite dimensional symmetry here, because the stress tensor is responsible for conformal symmetry, which in general dimension is SOD, 2, but we have infinitely many currents, so there must be some infinite dimensional symmetry that they give rise to, and this is known as higher spin symmetry. But the problem with higher spin symmetry is that that's it. So if you have free scalar or free Fermi, you have infinitely many of conserved currents. They give you some infinite dimensional symmetry that extends the conformal one, but free CFTs are the only models where you can have that. So it was shown, say, in 3 dimensions by Maldacena and Zhiboyedov, and with Boulanger, Terona, and Mitya in the audience, and myself, we extended this to NET greater or equal than 3. So the technical details don't matter, but just if you have conformal field theory in dimension greater than 2, and you find at least one conserved current, so you don't know what it is made of, just please find one conserved higher spin current, then you can actually show that there are infinitely many of such currents, and they are really made of free fields. So all correlation functions look like in free CFT. So in this sense, higher spin symmetry, unless you do something to it, is very boring, because it can only exist in free conformal field theories. So another example of free CFT is free fermion, and it looks almost the same. So you have the very first member, which is psi bar psi. Then you can have spin 1 current, spin 2 current, which is stress tensor, and so on. All of them are conserved. Okay, so the only difference between these two models, if you're only interested in this strange family of bilinear operators, is that the dimension of this first guy is 1 here, and it is equal to 2 here. Otherwise, they look the same. You just have conserved tensors of all ranks. So this is the only difference. So now, there are more interesting models of the same type, and where we have horizon, like this line. Okay, so the famous Ising universality class, or the CFT is also called Wilson-Fisher. It's also known as a critical vector model. So it's obtained as a fixed point under this double trace deformation. And this CFTs in general are very interacting, so it's hard to say anything about it. That's why people developed various expansion schemes, and for me the best expansion scheme is the large N. So how to get to large N is the usual trick is you do Hubbard-Stratanovich transform, so you just trivially rewrite this quartic interaction by introducing auxiliary field, so that you integrate over sigma in the path integral, and you get something like this. And then there are arguments why you can drop this term, and then you have a strange action with phi, no kinetic term for sigma, which is also a field, and phi squared. And there is a whole science how to make sense out of this action, but it doesn't matter right now how the technical details go. So you should be computing path integral like this. Yeah, but what's important is that this action does give a description of the Ising-Wilson-Fisher CFT in the large N limit. And then, if we take N be strictly infinite, what we see is doesn't differ much from what you see on this blackboard. So the dimension of operator sigma will be 2 plus 1 over n corrections. So then you can have your spin 1 current, spin 2 current, and all other currents, and they have expressions which are identical to those on the left blackboard, and they're also conserved in the strict large n limit. So if you depart from n equal infinity point, then currents are no longer conserved. In particular, all these currents have some anomalous dimension, which is of order 1 over n. And this is what is interesting to compute in these models. In all CFTs, so maybe correlation functions are hard, but the simplest number that you can extract out of CFT is a conformal dimension. So you know the engineering dimension, so the most interesting number is anomalous dimension. But you see that again, if the only operators you're interested in these models are these guys, it looks like a critical vector model that contains only bosonic matter looks a bit like free fermion, which contains only fermionic matter. So the dimension of the first guy in the family is 2, and then you have your higher spin currents. But here it's kind of trivial exercise to see that it's directed 2, while here 2 is actually, you can think of this as very large anomalous dimension, which is of order 1 that was somehow added to this sigma guy as a result of infinite summation of some diagrams. So it's non-trivial effect here, but still it's 2 plus corrections. There you have no corrections. Here you do have corrections. And another model, which is yes. I don't know who is first. Do you have hierarchy?
Students first.
Students first.
Why did you neglect? Why did you write J0 over there? Like it seems like you replaced J0 with sigma.
Yes, you're right. So, so there is operator phi sigma, but I mean, if you say don't neglect this term, then what is phi squared is actually sigma. The equation of motion for sigma tells you that sigma is phi squared. So this J naught guy is phi squared, and which is the same as sigma. But what's important is that it has very large dimensions. So if it were a free CFT or something very close to free CFT, free scalar CFT, then we know the dimension of phi squared is 1. Here you see a huge quantum effect, and then it changes into 2 instead of 1. Yeah, so yes, I forgot about it.
It's fine. No, it's fine.
Okay, so you just so then there is a fourth model of the same type, which is called gross nivel. We can also call it critical fermion, while this one you can call critical boson, like free boson, critical boson, free fermion, critical fermion. So four models. So it looks very similar. So you have fermion, and then you add quartic interaction, and then you treat it the same way by adding Hubbard-Stratanovich field, and then some magic happens that you can drop this sigma squared term in the action. So now the only difference is that the dimension of psi bar psi was 2 in free fermion, but right now the dimension of the sigma that plays role of psi bar psi is 1 plus 1 over n corrections. And again, you have all your higher spin currents, which in the strict large n limit do are conserved, but otherwise they have some anomalous dimension for order 1 over n. So, okay, we have these 4 models, and so the only thing you
Why
need...
is delta psi 1 now? I mean, delta sigma equals to 1? I mean, previously the logic was that it was the same dimension as phi squared.
Wait. No. Dimension of phi squared in free scalar is 1. 1/2 plus 1/2. 1.
Right.
But dimension of sigma, which is the same as phi squared, but now you have some interactions, is 2 plus 1 over n corrections. So, and here again, so you jump from 2 to 1, and here the opposite happens. From 1, you jump to 2. So this is the quantity effect. So now we know what matter is. And so let's just add Chern-Simons, which is very easy. So whenever you see derivative, you covariantize it, and to an action, which is one of these actions, you just add the Chern-Simons term. So we have four models like this, k over 4 pi if you wish, then Chern-Simons action for connection A and plus any of these. So, for example, dA pi squared or dA pi squared plus sigma phi squared. And cross the. That's it. So what's nice is that we have an additional parameter here. So right now we have two parameters, number of fields and k. And if you do large n expansion, then a common thing to do is to redefine your coupling constant and introduce what people call 't Hooft coupling. So here it can be shown that the role of 't Hooft coupling of just very nice coupling constant is played by n over k. So then what you see is that when k is infinite, then this term decouples. So it just tells you that A is any flat connection. It knows nothing about this interaction terms except that it imposes the singlet constraint. So now it makes sense to consider, say, bilinear operators or quartic operators, something that has all the indices contracted. This is what effectively Chern-Simons term does for you when k is infinite. When k is not infinite, they start to interact somehow with each other. And so the point being is that all these four theories are now highly interacting, not only because of that, but also because of that. So now even the free boson is not free anymore. It's now trivial CFT. Which has two parameters here, and now higher spin currents are not conserved anymore. In all four theories, they don't conserve. And we have the simplest four families of Chern-Simons meta theories. So it's highly non-trivial to have family of conformal theories because we need to have something that is strictly marginal, not marginally relevant or relevant, strictly marginal. Now this happens thanks to Chern-Simons term.
You take the gauge group to be simple, I guess, here.
Yeah, I'm just working with ON or UN.
And moreover, you take the matter fields to be in the fundamental of that one single group.
Exactly. So I have very small field content. So in APJ or APGM, you would take fields to be in bi-fundamental of two gauge groups. So your field is actually a matrix. You have many more fields. You can form many more operators. These CFTs are the smallest ones you can construct in, say, 3 dimensions. They just have vector-like matter. That's why we end up having just infinite family of these single trace operators, they call them in this CFT context. So, okay, we have 4 non-trivial CFTs, and now I'm coming to bosonization. So I gave a talk a year or 2 ago, so I don't want to repeat the whole thing, so just summary. I don't expect you to remember or be there, but I also don't want to repeat entirely what I said. So you have 4 families, and it makes sense to put them as points on this diagram. So here, for example, is free boson. It was free boson, now free fermion. Here it's critical fermion and gross nivel. And here we have critical boson of Wilson-Fisher. So these are 4 isolated CFTs that I just described. Now let's have Chern-Simons interaction. Because in the large n limit, this lambda becomes effectively continuous parameter, you have a continuous family of conformal field theories. And in principle, once you have lambda, okay, you can have your 4 families. They can go in any direction. So I don't have any axis here, so the direction means nothing. But what people noticed is that what they conjecture is that these 2 families are actually identical CFTs. So you might think that free boson with Chern-Simons is one permit a family of conformal field series that goes somewhere else. But no, when lambda is infinite, it ends at something that looks exactly like Gross-Neveu. And the other way around, if you start with Gross-Neveu at Chern-Simons interactions, so then you go all the way to free boson. And in fact, what the three-dimensional bosonization conjecture is about is that all the way along this line, these are identical conformal field series. So if you compute anything, like anomalous dimension of this higher-spin currents or correlation function, they should agree, they should coincide. Provided, of course, you know how to identify these two numbers. So you have, say, in the model with fermionic matter, lambda f and f, and in the model with bosonic matter, lambda b and b. So you should know how to map these two numbers, and then all correlation functions, all anomalous dimensions should agree. So likewise here, the conjecture is that these two families is actually one family, but just two equivalent description of this family of conformal field theories in 3 dimensions. Very good. And also, we know that it makes sense to say that, say, critical boson of Wilson-Fisher is a result of RG flow from free boson once you have this quantic interaction. And here, the situation is actually that you have a UV fixed point, which is a non-trivial one, Gross-Neveu, and if you add some interaction, then it flows to something that looks like free fermion. So it makes sense to connect these CFTs by lines which are G flows, but it's hard to describe what happens along the way. So because only the end points or starting points are conformal to the theories.
What is the operator you add to Gross-Neveu?
Let me see. I should know that.
Do you just add a sigma square?
Yes, I think sigma squared is the only relevant one. Yeah, it has dimension 1, so sigma squared is 2. Yeah, this you're right. Sigma squared is the only relevant. And then it flows to free fermion. Okay, good. So we have four families, but now there are two. The conjecture is that in nature you have only 2 families, and it's very hard to prove this conjecture because you have many interactions here. Moreover, because it's a gauge theory, you need fixed gauge, and the way that people like to compute in Chern-Simons is that they impose light congauge, so even covariance is lost. So to compute anything in this model is very painful.
Where did you say where they come?
What?
Why? Oh,
yes, to cancel the cubic piece you usually impose light congauge, but it doesn't really help much because you lose covariance, so you have to check it later, and also there are other interactions at other places. So what has been checked actually? So in this pure, so to say, CFTs, this one and this one, we computed anomalous dimensions of these currents just by using action that I wrote there up toward the 1 over n squares, because 1 over n corrections are kind of trivial. They're not 0, but they're trivial to compute, and actually you can see that anomalous dimensions of higher-spin currents in Wilson-Fisher and Gross-Neveu are exactly the same. So you can start thinking that this is the same CFT, but no. If you go to next order, which is very hard, it's 5 or 4 computations depending on the model, then anomalous dimensions are different. So then here, along this line, not much has been done, but in the paper with John B. Prakash, and Guru Charan, myself. So we computed anomalous dimensions of all these higher-spin currents toward the 1 over n, so which is the leading order where you expect to see anything interesting in all the 4 models using a combination of tricks. that I don't have time to describe. And we found that they do agree. So I think this is the only detail checked in this reality so far. Because when n is small, you can't actually compute anything. So the only regime is when n is large. And then I think what people computed are like thermal energy and anomalous dimension. That's it.
Would you recommend to some strong graduate student here to compute this to 1 over n squared or the 1
No,
over
I
n
don't, because because I did both. So and
Oh.
I know that we used very sophisticated techniques here because we did not break covariance and it was not a gauge theory. It was just the usual meta theory. And none of these sophisticated techniques survives once you have Chern-Simons, impose light conjugation, and so on. So I think it's just nightmare. So there is I'm not aware of any analytical methods that would allow you to compute here to the next order, which would be great. Because as I tell you, there is some degeneracy here that you can see even without Chern-Simons method. But when we computed anomalous dimensions and all these four theories, there is also some degeneracy left. You can see that there is something common among all the four guys. So if you just look at anomalous dimensions, there are some crazy functions and some structures that depend on the 't Hooft coupling constant, and they are more or less the same. So we can make it more precise. But so to the lead order, you do have non-trivial test, but still you don't quite distinguish between all the four models, which would be nice.
What is the dependence on k and n, your anomalous dimension? Exactly?
Okay, so then, yeah, so I'm coming to that. So you have this 't Hooft coupling constant, and then as a result of, again, infinite resummation of diagrams, you end up with two parameters which kind of effective number of degrees of freedom and effective 't Hooft coupling. So I don't actually remember how they exactly look like, but something like this. And lambda, I don't remember, I forgot. So you see that because if you Taylor expand scene, you see infinitely many terms. This result was the result of infinite resummation of some diagrams. And typical anomalous dimension would look like, so if you introduce new parameter which I actually like, so I so by lambda effective over 2, then anomalous dimension has very nice structures like cosinus squared, maybe sine squared of this, and then some crazy function that depends on spin plus g of s. I don't remember. This is kind of pattern you get. So and this is very interesting because here we have many diagrams, infinitely many. All covariance is broken, but once you get to the final answer, you see very nice pattern that you have kind of effective number of degrees of freedom, and then instead of this 't Hooft coupling, you introduce kind of an angle, and then whatever you compute in these models has this kind of form of trigonometric function, which we remember that theta comes from infinite number of diagrams times some functions of speed. Now I'm coming to new things. So the last result I want to mention.
No, not there, not there.
What?
The line is there.
There's a line.
Ah, I saw. Oh, okay. Oops.
Remove the camera.
So the last result I want to mention, and this is the starting point. Bootstrap idea here.
So there's no limit in which anomalous dimension goes to 0?
No, there is. So it's 1 over n stays the sum of it.
So until it goes to infinity is a good limit?
So when n goes to infinity, until it goes to infinity, and then you have this strict n equal infinity limit where everything looks like a free CFT. So you just have some strange guy sigma here with dimension 2, which you don't see in free CFT, but otherwise it looks like free CFT. Okay, so then the last very powerful result is that was obtained by Maldacena and Zhiboyedov. So they noticed that we know that the simplest operators here are higher spin currents, and to the leading order they are conserved, but then they don't. They must not be conserved if you have non-trivial conformal field theory. So then it's interesting to see what stays on the right-hand side, because we have a conformal field theory. So what stays on the right-hand side, what measures non-conservation, must be some conformal operator. So, and you can see that this operator looks like this. So I'm not writing indices. In practice, this expression means that you have some over spins here with the derivatives sticking around, but and coefficients here are mostly fixed by conformal symmetry, by the fact that you want this to be quasi-primary operator. But there are also some relative coefficients between different structures which are already quasi-primaries, and this is what is supposed to be fixed by broken higher spin symmetry. So they just noticed that in non-trivial CFTs of vector model type, including Chern-Simons meta-theories, non-conservation of current has a very special form. So what stays on the right-hand side is not some new random operator that you've never seen before and then you know nothing about it. It's cooked up from the currents themselves. And there are many nice tricks how to use this knowledge. So in particular, they managed to fix the form of 3-point functions. So we have infinitely many of 3-point functions, 3 times infinite family, and we want to know how they look like in principle. And one general result that has nothing to do with any of these theories, but just the consequence of conformal symmetry, is that there are 3 independent structures given 3 spins. There are 3 independent structures that you can put here. For example, you can take just 3 scalar CFT where you do have conserved higher spin currents, compute what this correlation function is, so you get one structure. So then you can do the same with free fermion, and what you get is completely different structure, not the same. If you are in 2 dimensions, it would be the same. But in 3 dimensions or higher dimensions, conformal symmetry doesn't quite fix. Even 3-point functions, there is some finite dimensional ambiguity left. And what was surprising is that you can also have 3rd structure, which is not obtainable from any free CFT, and it was called odd, first of all because it breaks parity, and this is what you expect from Chern-Simons, but also it's odd because there was not any simple way to get it. So you can just write the most general answers for 3 given spins, impose conservation, subtract these guys, and then you see that something is still there. So it was called odd. So it wasn't, until recently, it wasn't even know how it looks like except for some examples with particular spins. So nevertheless, these smart guys, using this equation, they found that 3-point functions must have this form. Cosinus squared, and cos sin here. So this result is amazing for several reasons. First of all, since we have 3 times infinite family of correlation functions, you can imagine some function of spins here, some function of spins here, some function of spins here. But what they could show is that there are only 2 parameters left out of infinitely many parameters. You can see that only 2 remains. That was first nice result. The second nice result was that here you're just using this equation in general results from conformal field theories, namely how these structures look like. Nothing else. In particular, you don't ask whether these currents are made out of fermions or bosons. You absolutely don't need this information to fix the form of correlation function. And now we see why bosonization can be true. It's because this result is obtained irrespective of whether J is made out of phi or psi. So this is true in nature. And then if you start from free boson, then of course theta is 0. These structures are dead, but once you go from theta 0 to pi half, you see a mixture of odd piece and free fermion piece, and once you reach pi half, you are here, and then you see that all these structures are dead, and you see free fermion correlation function. Very nice. So you see how bosons turn into fermions. But also it's amazing because if you try to compute it in Chern-Simons meta series just from an action, it's a mess, and only at the very end you can see that it combines into some nice expressions like this. So apparently, I mean, there must be something deep about it. So you don't need action at all. So there must be a way to avoid action at all, especially in view of the fact that action with bosons or with fermions are supposed to describe the same physics. Okay, now what's new? So I took this result very serious. Yes.
Is it true that those like building blocks, they're all identical concerns? Right?
Oh, what?
Identical concerns.
Good point. Yes, so you quote me in the sense that I just told you that currents are not conserved, but indeed structures obtained from free boson or free fermion are identically conserved. The one that is not identically conserved is this one. So, okay. So what's interesting we can do about it? So the idea was that we know that light-cone approach, light-cone gauge, has always been very useful. So strings were first quantized in the light-cone. Superring Mills and equal 4 was first proven to be finite in the light-cone gauge. So there is something nice about light-cone gauge. So what's nice is that first of all, you're dealing just directly with physical degrees of freedom, avoiding all these gauge artifacts, all this garbage that usually accompanies covariant description. I'm sorry for those who, yeah, I also fond of covariant description, but in the light-cone gauge, you're working directly with physical degrees of freedom. So the second thing is that what you're trying to do in the light-cone gauge, you usually directly construct generators of the algebra you're interested in. For example, when we could quantize string, we just construct generators of Poincare algebra and prove that they actually form Poincare algebra, and then all this intercept dimension is fixed just by carefully looking at the commutator. Okay, so and what I want to do is to apply this idea to not to Poincare algebra, but to conformal algebra. So why not? And because conformal algebra is the same time entity sitter algebra, and we have ideas CFT and so on, this is where I start talking about higher spins a little bit. So you can have two results for free, in the sense that if you manage to do something about conformal or entity sitter algebra in ADS, then you have some result in ADS, but also you can say a few things about CFT by computing correlation functions. So this is the idea. Namely, the idea is that let's impose light-cone gauge everywhere. So if you are in CFT, imposing light-cone gauge is equivalent to just solving conservation law, whenever you can do that. And you can see that in general, in 3 dimensions, of course, this tensor contains many components, but if you solve conservation law, you see that only 2 are independent. And just by looking at how conformal algebra acts on it, you can combine them into 2 scalars which have sort of definite helicity. You can make sense out of it. So tensor turns into just 2 scalars. So then we know that, of course, tensors, this is like CFT3 side. So if you go to ADS 4 description of the same quantities, then tensor fields, tensor operators are dual to tensor fields, and conserved currents should be dual to gauge fields. So what's dual to conservation law is gauge symmetry. So tensor, stress tensor is dual to graviton, and so on. And again, if you impose light-cone gauge here, then you end up with just 2 components, just 2 scalar fields, which have definite helicity. And because of ADS CFT, these are almost identical things, because you can always solve for the bulk field by saying that it's the boundary field times bulk to bulk propagator, boundary to bulk propagator. So there is some integral here, which actually not an integral if you go to momentum space. So just algebraic formula. You can always express the bulk field as some function which is about the boundary propagator times operator on the safety side. And now what I'm asking is whether we can construct generators of conformal algebra, which due to this formula is the same as generators of anti-de-Sitter algebra. In fact, algebras are the same, just variables are slightly different. So if we can construct nonlinear realization in the sense that our generators will be nonlinear, I don't have oscillators here for you. What replaces them are these fields. So if you wish, you can decompose them into oscillators. Box phi equals 0, you can solve it, you will see oscillators. So I'm not working with oscillators, I'm working with fields directly. And just because you have phi box plus cosmological constant phi type of action, you can see that there is a canonical, Poisson bracket here, something like this. Helicity mu, helicity lambda, then it's proportional to delta mu minus lambda and times some delta functions and so on. So you have a canonical Poisson bracket, this is your starting point. And then charges of whatever algebra, they look like phi, something bilinear phi, which comes just from free action. So charges in free in free theory are bilinear in your field, so this has nothing to do with the light convection, this is always true. And then we should be constructing first cubic and maybe quartic corrections to the charges, while the condition we would like to impose is that these charges, when you commute them using this Poisson bracket, form the algebra you want. In this case, we want this to be anti-de-Sitter or conformal algebra. And now,
which generators do you in particular pick up? In the light conjugation, usually, many of the generators don't create any problem.
oh, thank you very much.
But there's only those usually in some direction that are dangerous.
Yes, yes, exactly.
And
so
is that also
thanks
here?
for
Yeah.
mentioning this.
Yeah.
So indeed, you can think that, okay, Poincare algebra has how many? 10 generators, oh my god, I have to construct 10 generators by hand, this is crazy. But no, in fact, most of them, they stay quadratic in the fields, they don't receive any corrections from interactions at all. If you think about 4 dimensions, then your problem is only about 3 generators. Say in Poincare case, we have Hamiltonian and 2 boost generators, J, I don't know, A plus. So there are two of those. And the same number you have if you think about anti-de-Sitter or conformal algebra in the respective dimensions. So you also have to take care of just 3 generators. So it's not that crazy. And there is one guy who is expert and did many works on that inside. Yeah,
Are they subalgebra of Lorentz algebra, part of the ADS algebra, or?
No, it's mixed. So basically, if you think about CFT, then what you need to construct some part of boost generators.
They mix with translation, I think. Yeah.
They mix. But
Okay.
I mean, I can tell you. But the problem with the LightCon approach is that there's too much of notation. Your coordinates are broken into x plus, x minus the rest. The same is about fields and many other things. So I skip that. So I'm just telling you what is the general strategy. And the general strategy is that I will have to go through 4-dimensional flat space. Just, okay, you will see why. So here we have Poincare algebra, 10 generators, ADS algebra, 10 generators, and conformal algebra in 3-dimensional also 10 generators. So the thing is that if you think about fields, massless fields in 4-dimensional flat space, there are many papers, in particular by this person inside, who classified all possible interactions. So he classified all possible cubic deformations of the algebra. And in flat space, they look very simple. And in principle, you know them. These are just your cubic vertices that you can construct out of fields with definite helicity. So for example, if you have spin 1 fields, then phi plus minus 1, then there is interaction of phi plus 1, phi minus 1, plus 1, minus 1, and then also minus, minus, plus. And I'm not writing what actually the vertex is, because This requires a lot of light connotation. So if you take just free field and add this cubic interaction, you get self-dual Young-Mills, obviously. Then but this theory is non-unitary. If you add them up, then your Poincare algebra doesn't close, but you have your usual, say, Young-Mills vertex. But what can cure is adding some quartic interaction of this type, and then your Hamiltonian is no more than quartic in the fields, and if you go back to the action, you see just Young-Mills action and the light convergence. This is how you can bootstrap or discover any theories you already know, but so we would like to do something new. So what this guy did is that he classified all possible cubic deformations of the Poincare algebra, and this turns out to be in one-to-one correspondence with vertices that you see in the spinor helicity approach, which of course is not surprising, but it's kind of nice. Okay, so then the recent result by Tsaev was that there is some uplift of all these guys to radius 4. So the expressions are more messy than in flat space, but the result is the same. To each, say, spinor helicity structure here, or cubic deformation of Poincare algebra here, there is some structure in radius 4, which is just slightly more complicated, and the leading term is exactly the same. So you have this one-to-one correspondence between spinor helicity vertices and cubic interactions in ADS, which in particular what Mitya with someone here did. Also, okay, so you have these cubic deformations, and what's nice is that this guy also managed to get some constraints from the quartic order, because you have this, say, holomorphic and anti-holomorphic vertices that are expressed in terms of this square and angle brackets, and you put some structure constants, some yet unknown numbers, sorry, that depend on the helicity of the fields that stay here, so and then complex conjugate. So, and then you would like this cubic thing, this cubic generator to still form Poincare algebra. Then you get constraints from the closure of type CC or C bar, and also CC bar. And what's amazing is that these constraints have a unique solution. So there is some number here, and then just some of the helicities. So you can fix all your cubic deformations just in terms of one coupling constant for, say, holomorphic ones, and the same for anti-holomorphic with a priori different coupling constant. So if you want your theory to be Hermitian, then like we did in the Young-Mills, you have to add these two guys, otherwise it's not Hermitian. But then you run into the problem that you get this equation that is very hard to solve. But what we notice with MIT is that if you simply set C or C bar to 0, then you have your full Poincare algebra. And this makes some higher spin theory in Minkowski 4. But okay, let's jump to ADS. It happens so that in ADS, the deformations are more complicated than in flat space, but still the leading terms are the same. So you still get this result that cubic deformation of Hamiltonian, oops, this I don't want to, okay, perhaps this one. So you still fix all cubic deformations in terms of just two coupling constants. And this solution is known to be unique. So now the problem is that where this additional parameter that I called theta here, or lambda, where it is, because it seems to be that you just have one coupling constant, which is an overall number, while the structure we want to see here is a bit more complicated than just an overall number. So right now what I have is, so let me write any generator that has the following form. So there is something bilinear in the field. sum over all helicities, and I sum over all helicities because I'm only interested in theories that have all higher spin currents. Otherwise, if I restrict myself to something with the lower helicity, then I would be bootstrapping gravity, Yang-Mills, or something like that. So then there are interactions of holomorphic type. I'm not writing this, and anti-holomorphic. So if you take the flat limit, then they correspond to this angle or square brackets. But in EDS, it's hard to say what they correspond to. Okay, and then the trick is that you can get this parameter for free if you just do U1 duality rotation. Take the field with helicity lambda, then plus minus lambda, then rotate it by just phase factor, and plug it in back. So it looks like a harmless redefinition of your variables, but if you go back to, say, covariant description, what you have is a completely different action, because this thing has nothing to do with field redefinitions and so on. And let me just state the final result, because I don't want to go into the technical details of the light cone approach. So just starting from this very old deformation of Metsayev in the flat four-dimensional space, uplifting it to ADS, and then going back to CFT, what we have is our expressions for all generators of conformal algebra in terms of primary operators. And because of the use of ADS CFT, we can also compute all 3-point functions, for example. Okay, so let us. So first of all, okay, we have the relation of SO3 in terms of these higher spin currents. That's first thing. Then these chiral anti-chiral solutions, where you set either C or C bar to 0, give you completely two new solutions for 3-point functions. They were not found by Moldasen and Zhiboyedov, they missed them, but for a good reason, because these are non-unitary solutions. But I mean, these days people study things that are called fishnet theories, and they look very similar to what you get here. So first of all, you have two new solutions for 3-point functions. Then, if you add these solutions to each other as to get something unitary and introduce the parameter in a very smart way, then you have all 3-point functions of Chern-Simons meta theories. And because there is just one way how to make things unitary while still introducing new parameter, you're proving 3-dimensional bosonization to this order. Because let me just stress that at the time they got this result, even this structure was not known. So what they actually did, they took few of the lower spin currents, used this non-conservation equation, and obtained this formula, which was then conjectured to be true for all spins. But right now you can prove that it is true for all spins, and you can also get explicit formula for all of these guys, which we are now. Okay, so then just conceptually, what's nice is that spinor helicity classification of cubic amplitudes in flat space extends to ADS, and then each of these structures, upon plugging in bulk-to-boundary propagators, give rise to some CFT structure, which again gives you slightly more structures that people seen before, just because they implicitly they imposed unitarity. Yes?
More questions now. So earlier I wasn't going to bother you about the range of theta, but this is actually a U1 phase.
Mm-hmm.
And now you're saying that theta is the theta from that equation.
Yes, exactly.
But in that previous thing, there was the lambda, was cosine theta.
Yes.
So basically it could be negative, could be 0, could be anything.
Who?
Lambda, tilde, whatever it was. Lambda tilde was like cosine theta, right?
Yeah. Yes, there was cosine theta, and
It was like
it
pi
was
lambda over 2. pi lambda total.
Wait, so maybe I made a mistake here. So it was 1 plus lambda squared.
Oh.
Yeah, and this lambda tilde, don't take it seriously. There is highly non-linear formula for this lambda tilde in terms of your microscopical coupling constant n and k. So it is a result of infinite resummation of diagrams. So the nice variable theta, in terms of these microscopical numbers, I'll just say, it's the expression for theta in terms of microscopical parameters is highly non-trivial.
Okay, I was worried about the ranges.
Yeah.
Because cosine is between 1 and minus 1. What does this mean for lambda?
So lambda goes, say, from 0 to infinity, then you get your cosine.
Okay. And then separately in
Yes.
in the helicity formulas, and this is just a phase. This is just like it's like a gauge symmetry.
Yes, exactly. So, but the problem is that, okay, first of all, it doesn't affect scalar at all, but when you come to spinning fields where it does something, you can't write this duality transformation in terms of your gauge field. If you take a mu, you don't know how to write it, right? And then what happens is that if you write some covariant expression, say for an action in ADS that computes these correlation functions upon plugging the boundary propagators, then you have a family of actions that depend on this theta. And one action is just it's completely different from another one. It's not a filter definition, just because you can do this theta duality transformation in terms of, say, G mu, A mu, and all these higher spin fields. So so there must be some covariant formulas for, say, for an action of this theory where you don't have to impose Lightning gauge. But then theta enters non-trivially, and there is no way to understand it as a filter definition, just because this transformation you can't write as a filter definition unless you are in a Lightning.
In the bulk theory, what is selecting which boundary theory you're talking about?
So you have your spectrum, infinitely many of higher spin fields, each appearing once, and then you have a right to impose boundary condition, one or another. Then you capture in both cases. And theta in your action is just like additional coupling constant. But what's striking is that it's very easy to introduce theta in the Lightning gauge, while in covariant description, you just need to construct a family of actions, which are not redefinitions of each other. Okay, so then we know all these 3-point functions. We know how to introduce parameter, and there seems to be a unique way to do that, which proves Bosonization to this order. Because again, we are not asking what J is made of, bosons or fermions. We just say that we can prove that there is unique expression for 3-point functions. So if you find third Chern-Simons meta theory that looks like these two, then it has to give the same answer. Okay. Yeah, and then the last thing to mention is that everything seems to come from this 4-dimensional electromagnetic duality rotation, which is again very hard to see why it has to be so from a 3-dimensional CFT point of view. This I have no idea about what is the 3-dimensional reason for that, but in 4 dimensions it seems to be very easy to introduce this parameter. So let me stop here. I think I'm right on time. Thank you for your attention.
Any questions?
Statement that you wrote down about the tensor structures for the 3-point functions of current, is that true for your dimension, or is it true?
Okay, so what I can, so first of all, almost nothing is known about 4-point function, because here somehow there were nice ideas, but also 3-point functions are fixed up to a few numbers, where each 3 spins. So it was a kind of finite dimensional problem to solve. While 4-point function, you have these functions of conformal cross ratios, piling on top of the tensorial structures, which can also be quite messy. So I think Sasha Zhiboyedov with some guy, they bootstrap 4-point function of scalars. in one of these cases. Yeah, without actually Chern-Simons interaction, so you can see this nice structure. But I expect, and from this light cone point of view, it's very natural that if you need endpoint function, that you will just have sums of phase factors like that times certain structures, and then it's just particular case like the general pattern. And this is almost impossible to see from Chern-Simons action. Just no way.